Hi everyone, welcome back to Physics. Today we are going to be looking at the force of tension. Tension is a force arising from the intermolecular interactions of the molecules within a string or a cord that is stretched taut. So you might know from experience that if you pull a string or some cord to its maximum length, then you'll feel it become taut, which means that essentially these molecules are not going to be wanted to be stretched further than this maximum length. So what you get is going to be an inward pointing force on both sides of the string. So for instance, there's going to be some force acting from this side of the string, from this left side going right, and some other force acting from the right side, and it's going to be going left. And in most cases, where this cord is going to be massless, and if the situation is ideal, or near massless that is, and if the situation is ideal, these two forces will be the same, and we'll look more at that in a second. Consider this example right here of a block hanging off the ceiling from a taut cord. We know from experience, first of all, that the acceleration of this block should be 0. Because if we hang a block off a string on the ceiling and the string is stretched tight, as long as the string doesn't break, this block should not be moving, so its velocity is going to be a constant 0. So the acceleration of this block here is 0. We also know that there's going to be some downward force acting on this block that's caused by gravity, and this is going to be equal to F sub g equals mg. Well now, since this acceleration is 0, we can apply Newton's second law and say, well, that means there must be some upward force also acting on this block, also with magnitude mg, but actually a negative mg acting in the upward direction, to cancel out this and make the net acceleration 0. This force is caused by tension. So this tension is going to be exerting, the tension from this taut cord here is going to be going up, and it's going to, I'll label this as F sub t equals negative mg. And here we see we're drawing a little free body diagram here, which if you remember is just going to be a diagram where all the forces are drawn out and quantified. And to make things a little simpler, I'll try to color code some of the forces. So these red forces here represent the forces acting on this block, M. So now, since this cord here is going to be pulling upward on the block, that means the block must also be pulling downward on the cord, with by Newton's third law, with the same magnitude. So in blue here, I'm going to draw the force acting downward on the cord caused by the block, and this is going to be some mg again. It's just going to be the same magnitude as this force of tension, but in the opposite direction. But now, assuming that this cord here is fairly light, is very light, the mass is negligible. Let's say the mass is approximately 0. Well, since force equals mass times acceleration, that means that no matter what happens here, the net force on this block must be 0. And if this force is 0, then that means that there must also be some other force acting upward on this cord, as there's already some force acting downward. This is going to be caused by the interaction between the ceiling and the cord. And it's actually going to be some force over here. There's not much space here, but it's going to act upward on this cord with some negative mg. And meanwhile, the cord must also be pulling down on the ceiling in return with some, and I'm going to outline this in green because the green is what's acting on the ceiling here, and this is also going to equal mg. So here we see there are many forces at work here. They all have the same magnitude, and they're all one of two directions, so they're pretty similar forces. But we see there must be many forces at work acting between each of these interaction points in order to keep the entire system at equilibrium, or static equilibrium that is, which just means that nothing here is moving. Now let's look at another example with tension. Let's say that we have some string with some finite length, let's call it L, and it's going to be attached to a small ball here with mass m. And maybe you've seen some of these before, like we have a elastic string here with some length, and maybe you've spun this thing around. So say let's whirl this ball around in a circular path. like thus. Imagine that this is a circle with our hand or something, where our hand stays at rest, so our hand just stays in the center with our wrist rotating or something, and the ball moves with some velocity v, some constant velocity v, around this circle. So by experience, if you've ever done this, you might feel that the ball is trying to escape you or something. And this is somewhat true. There is going to be a force acting outward here, but if you remember from before, from our kinematics video, you might remember that an object moving in a circle actually is going to have some centripetal acceleration, which means an inward acting acceleration. And the acceleration of this centripetal force is going to be equal to v squared over r, where r is going to be the radius of rotation, or in this case, going to be L. So this acceleration equals v squared over L. That means that since force equals mass times acceleration, the force on this ball, the centripetal force on this ball, must be equal to mv squared over L. And this force is going to be caused by the tension within this string here. So let's outline this in red here. This inward force caused by tension is going to be some F sub t equals mv squared over L. And the important thing to remember here is that tension, unlike, say, gravity, which is always just going to be mg, doesn't really have a set formula to it. We can only really find tension by figuring out which accelerations must be acting on this object, and seeing if the tension actually causes this acceleration, and adjusting as such. So, for instance, here we see the tension actually equals gravity because it needs to counteract gravity. Here, the acceleration here is going to be v squared over L, so the force is mv squared over L, and we see tension must be the force causing this. There's no other magical force that's just making this ball move in a circle other than the tension from the cord pulling it inward at all points. So this force of tension here is going to be mv squared over L. And similarly, we know that there must be some outward pointing force here. And here my writing is starting to go on top of itself, so I'm going to try to move this out a little bit. This outward force here is going to be the ball actually pulling on this cord. Actually, I'm going to quickly change the position of this to like over here to show more properly that it's acting on the cord. The ball must be pulling outward on the cord with some other mv squared over L, but in this direction. And this is kind of bad notation because this here is a scalar value. Actually, this only represents the magnitude. This is also only representing the magnitude, but we can see from the vectors which directions it's acting in. Now again, we see the cord must have a net force of 0 if we assume that it's fairly light compared to the rest of the system. So that means there also must be some inward force acting on this cord here, so the net force is 0. And this inward force is also going to equal mv squared over L. This inward force is actually going to be your hand or whatever, or if there's some pivot here, that pivot pulling in on the cord. And in the case of your hand, well, we see if your hand is pulling in on the cord, then the cord must be pulling out on your hand. So there's going to be some other force from over here, also equal to mv squared over L, where the cord is pulling outward on your hand. And this is why you feel this outward pulling force whenever you spin this ball in a circle. Although the ball is actually being pulled towards you by tension, your hand is going to be being pulled outward by the tension, which is why you feel the outward force, but the ball feels an inward force. Now, one important thing to remember here, although you might feel a force going outward, if you let go of this string, the ball is not suddenly going to fly outward like this. The ball's velocity, remember, at any point on this circle is going to be tangent to this circle. So if you let go of this string, then this tension force will disappear, and the ball is actually going to fly tangent to the circle in this direction. So this is going to be incorrect, and this is going to be correct. If you you can try to test this. If we spin a ball in a circle, and we suddenly let go of it, the ball is going to be flying tangent to this original circular path.